All right, continue with the last topic tonight, which is arc energy and input. All right, before we start, I would like to explain from the whiteboard. It is, okay. So I'm going to discuss two things here about the heat input. We start with European, EN, European. All right, European says heat input equal to arc energy times thermal efficiency factor. Right. So here, arc energy equal to volt times amps divided by travel speed times 1000. And thermal efficiency factor depend on welding process. And they put it as a K. Thermal efficiency factor represented by K. Okay, K here depend on welding process. SAW equal to 1 MMA MIC MEC FCAW, all those equal to 0.8, TIG equal to 0.6. That's the K factor from different welding process. All right. 10 times with K. All right. So that's for European. American example in AWS or ASME, they mention like this: heat input equal to volt times amps divided by travel speed times times 1000. That's what in American. So the difference between these two, American and European, are the K factor, the thermal efficiency factor. European use K, American didn't use K. So in American, heat input, volt times M divided by travel speed. That's it. No K factor. European, yes, they have K factor for the heat input, which is from welding process. Clear about this? So in your exam or training, if they ask for arc energy means volt times M divided travel speed times 1000. That is arc energy in European. If the question asks heat input, then you need to times with K. Okay? Clear about this, yeah? Right. So don't worry too much about the American. For the American here, we're not using in our training and exam. Okay? So we use this. We're using this, arc energy or heat input. Remember, heat input, arc energy times K. Yeah? So arc energy itself, volt times M divided travel speed times 1000. Clear about this, yeah? Okay. So how to get travel speed? Travel speed we got from distance, which is in millimeter, divided by the time, which is in second. So that's how we got travel speed. Distance divided by time. Yeah? Okay? All right. Have you copied this one? Yeah? All right. But never mind, we also discussed from your slide. But this is the things you need to careful. Yeah? All right. The difference between American and European. All right, we talked from your slide about heat input and arc energy. All right, here, what are the factors that influence arc energy or heat input? Ampere, voltage, travel speed. Yeah. All right, what's the difference between arc energy and heat input? It's a thermal efficiency factor known as K. That's what in European. Ask me, call it heat input with no K. In this, ask me, heat input, no K factor. Yeah? It's measured as arc energy. In European, call it arc energy. All right. What we call arc energy in American refer to heat input. The different European and American is the use of thermal efficiency factor. In European, call it K. The K factor denotes the thermal efficiency value of welding process. So the amount of heat generated in welding up per unit length of weld expressed in kilojoule per millimeter, arc energy, kilojoule per millimeter, volt times M divided by welding speed or distance divided by time, and then we time 1000. Reason why we need to time 1000 here, because of we need to have unit in kilojoule here. So that's why we need to time 1000. That's the relation why we need to time 1000, because of the unit must be in kilojoule, not in joule, kilojoule. So that's why times 1000 here. All right, clear about this? The energy supplied by the welding arc to workpiece expressed in the terms of arc energy times thermal efficiency factor. All right, so memorize this one. What is thermal efficiency factor? Maybe they ask you about this. Memorize, highlight this. So thermal efficiency factor is the ratio of the heat energy introduced into weld to the electrical energy consumed by the arc. So what I said here is we have a cable here. All right. Okay, we have a cable. Right, this is the electrode. So they are talking about electrical energy consumed by the arc electrode and the heat energy produced. So what is the ratio? Electrical energy and the arc energy produced. Yeah, so that is the ratio here. Or another example, how much you eat, how much you go to toilet, how many times you go to toilet. Yeah. All right, so here, remember, it's not difficult to memorize. Okay, you need to memorize this. Eh? SAW1, TIG 0.6. Others, all 0.8. Okay, so that is easy. Yeah, so don't worry about what is K factor for MIG-MED. No, it's easy thing to memorize. SAW1, TIG 0.6, the rest all 0.8. Yeah, and remember, you also need to memorize all this. Yeah, all this. I think this one okay, but don't worry too much. 136, more than 136, all flash core. Yeah. Yeah. Memorize. All right. Now, example. In the MAC welding, the following condition were recorded. Arc voltage 24, current 240, traverse speed 300 per minute. Remember, we have minute here. So when we have minute here, we need to change to 60 seconds. Yeah? So the question asks, what is arc energy and the heat input? Right? So the arc energy, remember, in European, no K. Here, arc energy, no K factor. Okay, no K, no need. All right, volt times amps, all right, 24 times 240 divided by 300 divided by 60. I would like you to put 60, don't put it here. Straight away you times here. This is very quick calculation, very quick. All right, change 60 there, divided, make it times on the top. That's very quick calculation. Do it. You know, you need to do it like that. Okay, that's easy for you. Okay, and we got roughly about 1.2 kilojoule. This is arc energy. If we want to have heat input, then you need to times with MAG 0.8. Then you got lower value. Yeah, the value of this heat input will be lower than arc energy value because you need to times 0.8. Yeah? Example here, what is the heat input now? So you need to put 0.8 there. You see they use 60 there and then 0.8. So as a result, you got 0.92. So here, 1.2 times 0.8, you got 0.92 kilojoule for the heat input. Yeah? All right. And this one, we have stringer bit and comparing to weaving. Okay? So what will be the effects? If we have the heat input equal to, we know heat input arc energy times K. So now we have volt times amps divided by traverse speed, and then we got K. So if we use a stringer here, is it fast travel or slow travel? This is fast travel. When you have fast travel, you have fast travel here, travel speed fast. What happened to heat input? Lower. Yeah, clear about this? How about weaving here? It's fast or slow? It's a slow travel. So slow travel, what happened to the heat input?
It goes up.
You got slow travel, then the heat input will be higher. Okay? Right, so that's the thing we need to talk about when coming to travel speed. So you have slow travel speed, the heat input higher. You have fast travel speed, then the heat input will be lower. Okay? So that is comparing of stringer bead and weaving bead. And also, sometimes they ask you about this. All right, you have PF and PG position. PG, vertical down, PF, vertical up. PG, vertical down, this is fast travel. PF is slow travel. That will affect the heat input. The same thing we discussed about stringer bead and weaving. You got fast travel, slow travel. What will be the difference in heat input? Memorize this. This is the thing you need to memorize. Okay, changing of positions, changing travel speed, fast or slow, it will affect the heat input. Okay, stringer bead, weaving, PF position, PG position, what will be the effects to heat input? All right, you need to copy this and memorize. Okay, basically it's no need to memorize, just understand what's going on, all right? When you change the positions. All right, clear about this? Okay. All right, we move on to next slide. It's questions already. In near future, your shop floor is likely to get fabrication job involving many critical material, which controlling heat input will be required to achieve desired properties. The customer has already provided you with the specification, the CSWIP spec, which talk about welding of many materials, specify heat input control for some of them. It is generally fed by you and your team that proper understanding of this vital area is required. All right, look at question 1. This is no spec. 2, no spec. 3, yes, there is a spec required. 4, spec. 5, no spec. 6, spec. 7, spec. 8, spec. 9, spec. 10, spec. So I will repeat again. Question number 10, spec. 9, spec. 8, spec. 7, spec. 6, spec. 5, no spec. 4, spec. 3, spec. 2, no spec. 1, no spec. Right? Question 1. The question talk about arc energy. So we understand when they say arc energy mean there is no K. So what we have here, arc energy equal to 24 times 225 times 60 divided by 250 times 1000. So the answer must be A, yeah? All right, number 2, TIG using parameters 20 volt, 12550 millimeter, but now they ask for heat input. Then the K factor here for TIG is 0.6. So here, heat input equal to 20 times 125 times 60 divided by 50 times 1000, and then we times with 0.6. Yeah, so the answer should be C. Yeah, okay. Number 3, using the preheat tables, all right, in TWI spec, when welding carbon manganese, they having carbon 0.38, section combined thickness 25, using MMA process, hydrogen scale C. All right, and with the preheat 125, 22 volt, 150 amps, which welding speed? The question asks about welding speed. Then you need to times 1 by 1, calculate 1 by 1. Right. But before that, we check from table 2A. All right, here, table 2A. Carbon equivalent is 0.38, fall under here, and thickness, any thickness, temperature 1 to 5, and the heat input required is 0.522. Yeah, this is table we're looking for. Hydrogen scale C, 0.522. So from here, what you need to do is you need to calculate one by one. So 22 times 150 times 60 divided by, let's say that the answer given is D, then we do calculations, 80 times 1000. And then remember, MMA is 0.8 is the factor here. Then they ask for 0.522. So only D is the within the range. The rest all above than 2, like this. Yeah, so that's why all this is wrong. Okay. All right, number 4, the same thing. Here, carbon equivalent 0.4, combined section 102, preheat 50, MMA. All right, the same table. We're going to check from the same table what required heat input value. So we have preheat 50, thickness 80, which is more than 100. We got 102 in the equations. Any carbon equivalent less than 0.45 here, 50 degree. So required here is 3.0 to 4.1. 4.2 less than. So it must be 4.1 here. Yeah. The same thing. So we need to do from here, work out here. We got 24 times. The answer goes to A. So we times with 276 times 60 divided by 100 times 1000, and then we times with 0.8. So within the range only A, because the B also wrong because we got 4.3, C wrong because we got 6.4, and D is wrong because we got 5, which is more than 4.1 or 4.2 here. Okay? All right, number 5, which of the following is true? The lower heat input, higher preheat. That's correct. This is what we need to refer to, preheat. Preheat factor. Preheat factor is hydrogen, heat input, thickness, and carbon equivalent. Yeah? All right, the answer goes to A because lower heat input, then we got high preheat required, or maybe high preheat, lower, high heat input, lower preheat. Okay? B is wrong because the same method, the heat input increase with decreasing hydrogen level. There's no relation between talking about heat input and hydrogen level. Preheat increase, heat input increase was wrong because when the preheat increase, heat input will be lower. Yeah. All right, 6. Which of the following method have specific restriction? When talking about specific restriction, the answer goes to all of the above because we're going to check later from the spec on the page 29, 16.4, duplex, page 25, aluminium, page 27 and 28. They said here specific restriction means it must have minimum and maximum. All right, which of the four material has minimum and maximum heat input? All right, we check one by one. First, we start with page 29. On the page 29, table 6A, we can see here, they all mention about, from the preheat here, we can see that it's got different heat input value minimum. All right. All this table giving us the idea of value of the heat input. Mean there is a restriction. It cannot be anything, any heat input is not allowed. There is restriction there. All right. The second one, we look at page 25. Duplex stainless steel, 14.4. In 14.4, we can see that it depends on the chromium content. Then it will give minimum and maximum of the heat input value. Yeah. All right. For aluminum, look at page 27 and 28. For example, in this table 5A, we can see that for different thickness here, they give minimum and maximum for the heat input. There is a restriction for the heat input. All right. So that's where the answer goes to all of the above. Yeah. 7. Using TIG process welding 4043 aluminum, thickness 4.2. Which of the following parameter will be accepted? All right, again, look at page 5.8. All right, the thickness in the equations 4.2. The minimum heat input will be 0.89 and maximum 1.2. Then from there, the answer given is C. So when we calculate the answer C here, for TIG, the heat input equal to 21 times 30 times 60 divided by 25 times 1000, and this is TIG. The K factor is 0.6. Then we times with 0.6. So the answer we got from here is 0.9 kilojoule, which is within the range. Okay. 8. Welding 514 grade material. So 514 here is quench and temper steel material. Thickness 15, preheat 100 degree. Which of the following parameter acceptable? All right, then we look at on the page 29, table 6A. All right, from there, the preheat required is 100 degrees C, and the thickness between 12.5 to 25, then we can see that required heat input is 1.6. That's the minimum, all right? 1.6 is the minimum heat input. So the same thing, we do calculations, and C is the best answer because from there minimum we got is 1.6. This is less than minimum. So minimum required from the table is 1.6 kilojoule. If you do calculation, all this below then 1.6. Okay. Question 9. When welding duplex stainless steel, having 23.5 chromium using TIG process for plate 12 mm, the heat input will be dependent on, all right, look at 14.4. In 14.4 here, we can see that different chromium content here will give different heat input value. All right, heat input value here depend on chromium content. So that's why the best answer here goes to D. It's not from the carbon content, it's not from the preheat use, and it's not from the thickness. It depends on the chromium. All right. All right, last question, number 10. When welding 75 mm quench temper, preheat 100, the minimum heat input restricted to, all right, look at page 29, table 6A. Right here, table 6A. The thickness is 75. So when the thickness is 75, it's more than 50. So you got 4.8 kilojoule. Right, 4.8 kilojoule. So the answer given is C. Yeah? All right, guys, we finished the question and answer for 3 topics this morning. All right.